That's the beauty of National Lab. There is a huge interest and push towards adapting and using AI to accelerate scientific discovery. And in that context, the automated machine learning is something that is relevant for a wide range of applications.
Welcome to the Conversations on Applied AI podcast, where Justin Grammans and the team at Emerging Technologies North talk with experts in the fields of artificial intelligence and deep learning. In each episode, we cut through the hype and dive into how these technologies are being applied to real-world problems today. We hope that you find this episode educational and applicable to your industry and connect with us to learn more about our organization at appliedai.mn. Enjoy.
Welcome, everyone, to the Conversations on Applied AI podcast. Today, we're talking with Prasanna Balaprakash. Prasanna is a group leader and computer scientist at the Mathematics and Computer Science Division in the Leadership Computing Facility at Argonne National Laboratory. His research interests span the areas of machine learning, optimization, and high-performance computing. He is a recipient of the U.S. Department of Energy 2018 Early Career Award and is the Artificial Intelligence Thrust Lead at RAPIDS, the Department of Energy Computer Science Institute that assists application teams in overcoming computer science, data, and AI challenges. He is a principal investigator on several Department of Energy-funded projects that focus on the Department of Scalable machine learning methods for scientific and engineering applications. Prior to Argonne, Prasanna worked as a chief technology officer at Mentis, a machine learning startup in Brussels, Belgium. He received his PhD from Iridia, the AI lab at the ULB in Brussels, Belgium. Thanks, Prasanna, for being on the program today.
Thanks, Justin. Thanks for having me.
Excellent. Cool. I told a little bit of the listeners about your background, but maybe you can fill in some of the more details, like what was the trajectory of your career to sort of get you interested in this field and then kind of lead you to where you are today.
I did my undergrad in India, and then I moved to Germany for my master's, and then later to Belgium for my PhD. And during my PhD, I was involved in the design and development of sort of algorithms, automated algorithms for designing other algorithms. And that's where, my interest in design automation and automated algorithms started. A lot of credit goes to my supervisors back in Belgium who sort of instilled this type of research into my career trajectory.
Yeah, sure. Well, algorithms assigning other algorithms, that sounds pretty meta, I guess. How does that work, I guess? Are you have to train these algorithms based on, were you actually like having code generate other code in some ways?
That's one part of it, right? So, there are several ways to think about this problem. As you said, it's a meta algorithm design problem where you have to sort of first think about what are the templates and what are the design choices that should go into a particular algorithm. Often, algorithm designers, as a computer scientist or computer engineers, they come up with some sort of algorithm based on their prior experience. And even inside the algorithm, they can think of different types of components. And often they have to pick one based on a particular problem that they are solving or the sort of test cases they have and sort of, fix that as a choice, as a decision choice instead of exploring all possible choices. The reason being that it's very, very difficult to explore all possible choices in a complex algorithm. Each algorithm can have different choices and each choices can sort of expose different parameters and so on and so forth. So all these sort of explode the number of design choices one need to explore in coming up with the right algorithm for the right problem. Even if they come up for one algorithm or for one setting, it is not generalizable to other settings, right? So that's where the whole problem of automated algorithm configuration comes in, where we say, okay, what am I setting? What are the sort of problem instances that I'm going to see? And based on that, how can I come up with a set of design choices for a particular algorithm that will work well for the particular class of instances and so on and so forth. So that's the sort of one way to look at this problem. And then you can even take one level up where you can put a sort of a reinforcement learning policy where you learn a policy that decide which choices that algorithm or what are the decision variables or the decision values that a particular algorithm needs to take based on the particular problem instance that it is seeing at that instant. So there are many flavors. As I said, it's a very complex problem, very challenging problem. And trying to automate these algorithms in a much more rigorous and systematic way is an open research. And there are a lot of interesting work happening in this domain, in particular, again, in the context of machine learning as well.
And so that's kind of what you focused your PhD on? Was this concept around this?
Yeah, that's one of the major topic of my PhD.
Yeah. I mean, I didn't mention it during the introduction, but you're instrumental to this DeepHyper project going on, correct?
Correct.
Could you tell us a little bit about that? I mean, this seems to sort of fall in line with what you did with your PhD.
During my PhD, was looking at the design and development or automating the design and development of heuristic algorithms. These are a class of AI algorithms to solve combinatorial optimization problems, which are one of the hardest problems to solve. The DeepHyper project is primarily focused on how we can design or how we can develop machine learning models. So if you think about neural networks, one of the most promising machine learning approaches, it comes with lots of hyperparameters, so to speak. What type of learning rate, so what learning rate to use, what type of optimizer, number of layers, number of units per layer, and the topology itself, what type of topology to design. Even if you think about convolutional neural network, you could always ask why this filter 5 by 5 over 3 by 3, right? So there is no sort of clear-cut answer for that. And often this is determined by some human expert based on some test cases they play with, right? And often one could improve the performance of these methods to a great extent by changing architectures, changing the optimizers, changing the learning rate, regularization, and so on and so forth. So neural networks, they provide powerful function approximation for many problems, but at the same time, it comes with a lot of complexities. And many times one needs to sort of, map or take these deep neural networks and adapt it to a particular data set. And that's typically trial and error process. It's okay, how can I change this and make it work? Or looking at the loss function and looking at the validation loss and see, okay, am I overfitting or underfitting? Okay, can I go and tinker this around and make the network learn well and so on and so forth, right? If you think about it, all this can be sort of encapsulated into the automated design problem where we can do this in a much more automated way and also in a much more rigorous and systematic way.
Yeah, for sure. You were talking about tinkering with things. So yeah, I do a fair amount of stuff with Google Colab, which are basically sort of like Jupyter notebooks, and there's when you start working with TensorFlow and sort of building these models, I mean, it's just, there's almost too many dials that you would want to be able to turn. It sounds like, you guys are trying to automate. And I was thinking about too, like Google has this concept called AutoML, right? Is that what this project is sort of based around? Is it a competing project to that? I know yours is open source too, and I'll be sharing links to all of that, but kind of a lot of things wrapped up in my mind right now as you're sort of like talking through, but that's the general gist of what you guys are doing there?
Yeah, at a high level, we are all trying to solve a similar set of problems. The way that DeepHyper sort of different from AutoML from Google is that, we primarily focus on scientific applications. And also we focus on solving problem at scale. We have access to some of the fastest supercomputers on the planet. And how we are trying to solve this problem is to scale up AutoML in a way that we can reduce the time to develop these models. And also our focus is incorporating scientific domain knowledge into those models and how we can automate that process, right? So if you're talking about solving or developing a surrogate model for a scientific application, there are a lot of physics knowledge that comes with it. A promising approach to incorporate the existing physics knowledge into the deep learning models is to add them as a constraints, as soft constraints in the loss function and so on. So it's great. This is the design philosophy behind physics-informed neural networks. But once you start adding these constraints into those loss functions or in the architectures, your training loss surface becomes really, really difficult to navigate. So any sort of optimizer that you throw there will have problem. And there is a lot of interesting research happening in that space, how to address this problem and so on and so forth, right? But we take this idea of, okay, how to incorporate these physics constraints into loss functions. And if we do so, how that affects this architecture and how we can adapt this architecture. So think of ways in which we can put residual connections to make loss surface much more smoother and how we can adapt learning rate to cope up with that sort of rugged loss surface. And all these things, even for the non-scientific problem with the regular loss function, you have to think of so many parameters, but now add to this complexity, this physics knowledge, the physics constraints and so on and so forth. That just blows up the complexity even further. And the class of problems that we deal with, it's not just image or text. There are a lot of problems that we have to solve with graph neural networks. point clouds are manifolds, those type of input data sets, the diversity of the data across different scientific applications. And for each of them, think about ways that we have to customize these neural network models or general machine learning models. That's a very, very challenging problem. And one way that we are trying to address this problem is to sort of help the domain scientists to turbocharge the design and development of neural networks. So how can we automate these surrogate model developments or these neural network model developments for various types of data sets? And that's the core focus. And that's where we are specializing and helping domain scientists. So in that way, it's sort of different from AutoML from Google, where the focus is primarily on the commercial applications and images and text.
Yeah, no, I totally get that. So yeah, you guys are basically a Swiss knife, I guess, for people that are in the research domain space, right? It's completely different. Or a Swiss Army knife, I guess is the word that I would use, where they can basically use your tool to then focus on specific issues that they're running into, that they're trying to build out in the field. And, you're at the Argonne National Laboratory, I guess, kind of under the Department of Energy. Is that where a lot of the work that your programs are working on?
That is correct.
Yeah, cool. And so can you give me some examples? I think when we originally sort of started talking, you were talking about some ideas of accelerating weather simulations were some things that we maybe talked about. Or I love the idea of, disruption detection of fusion energy reactors. Speak to me about any, I guess, project that you'd like to with regards to maybe how this is being used by researchers.
There are multiple projects that are currently being benefited from the use of automated machine learning methods. And I would like to point out a few of them. One that you already mentioned, development of surrogate models for weather simulations. So weather simulations, ability to simulate the weather phenomena is critical for many different applications. And the way that we are looking at this problem is, there are two different approaches to do surrogate modeling for weather simulations. One is the intrusive way, where we say, here is a simulator and here are the most computationally expensive part of the simulator. And for your information, the simulations are very, very expensive. They take the entire supercomputer and run it for several days or even months at different resolutions and so on and so forth. So the intrusive way of attacking this problem is looking at what are the computationally expensive part of the simulation. And most of them are sort of related to solving PDEs, partial differential equations, and so on and so forth. And say, can we learn a function approximation to those type of computationally expensive modules? And if we can do that either offline or online, then we can reduce the computationally expensive part of the simulation by a large factor. And here we are talking about 100x speed up for those parts. And if we can do that, then there are multiple things that we can do on the top, right? So the simulation time will be drastically reduced. And if we can reduce that simulation time for the weather, then we can run not 5 or 10 ensembles, which are the current state of the art, so to speak. We can do thousands of ensembles with different initial conditions and at various resolutions. Those kind of things allows us to ask very interesting what-if questions with respect to the climate change and so on and so forth. And the non-intrusive one is trying to develop a surrogate for the entire simulator, taking the data from the entire simulation and sort of, matching that with the observations and calibrating the simulator with respect to the observations and using the sensitivity. For example, you cannot think of this complex code and computing derivatives of the variables from this complex code. Impossible. On the other hand, we can develop a surrogate to this entire simulator, or at least the major parts of the simulator, and then compute derivatives, or compute adjoints, and look at the sensitivity of those input parameters, which is otherwise impossible to verify. So there is a physics. Here is a physics model that is encapsulated in simulation. Now we have a surrogate and another computationally cheap model, which we can use to compute derivatives to analyze sensitivities of the variables, climate variables, and so on and so forth. And that has a huge, huge impact. Not just the known physics, but you can then match that with the real observations and try to see whether your physics model, what our human understanding of the physics model matches with the observations and where the mismatches are, and try to sort of improve the understanding going further. So those are all interesting questions that the surrogate models for weather simulations can enable. The second project, the fusion energy reactor, developing surrogate models, in particular, the disruption detection in in the fusion reactor. So we are working with our collaborators in Princeton, and we are looking at ways to develop models that can sort of look at the state of the plasma and trying to see whether this plasma is going to be stable or not. This is very, very critical because if you can detect precursors, or using these precursors, you can detect that the plasma is not going to be stable, and you can go and adjust the parameters of the reactor in such a way that this plasma becomes stable in the future time steps. Because once the plasma becomes unstable, then you have to switch off the reactor, and that has a huge overhead cost. And in fact, some of the recent work from DeepMind is looking at related problem, and they are using reinforcement learning to sort of control the stability of the plasma. So the problem is much, much more sort of complex. It has different flavors, and different reactors have different set of complexities. It's one of the grand challenge problems. If we manage to crack this, we almost address a lot of energy related challenges that we face today. So that's a very exciting project that we are involved in. And there, what we are trying to do is to develop these spatiotemporal deep learning models automatically. It's again a complex problem, complex model, complex data sets. And we are trying to help these domain scientists to automate the design and development of deep neural network models to detect the instabilities or the disruptions in the plasmas. There, the challenge is a little different. It's not like we can build a trillion parameter model to do that, because this will be deployed at the edge near the reactor. And here we are trying to not only reach accuracy, but also inference time and the model size. So it's a sort of a multi-objective automated machine learning problem where the goal is to build a neural network or a neural network model that will be small, efficient, low latency, low inference time, and we need high accuracy. So it's not about accuracy there. It's all the other metrics that makes this problem a lot more challenging. So that's another project that we are involved in. We are also, working with other teams where we are developing automated NLP techniques to analyze large amount of corpus, scientific articles, to extract information related to climate change and how the climate change is affecting or will affect the US infrastructure and how these things change over time and so on and so forth. This is primarily trying to help the decision and infrastructure team here at Argonne to sort of see, how they can consume really hundreds and hundreds of articles that are coming out and sort of synthesize that information and try to find what they are looking for. Again, we are trying to, automate this process of developing a natural language pipeline.
Yeah, there's a lot of written records, I'm guessing, around over the past 100 years, right? So not everything was stored on disk drives and stuff 100 years ago. So you're kind of trying to parse and go over all these articles, I'm guessing, right? There's a lot of, and probably a lot of, are you guys using a lot of OCR to sort of take a look at even images, or has a lot of it been put into digital format at least, but then you're trying to sort of read through and understand it?
So right now our focus is primarily on scientific articles. But as you said, there are many sort of written records. That's one of the sort of earlier challenge that we had to face and try to overcome. We haven't found really a clean-cut solution for that, and we are still working on it because, if the records on the infrastructure and if there is incident in that infrastructure, it's, those are all sort of captured in a written form, and ability to extract them and put them in a meaningful way or in a computable form. It's an open challenge that we have to overcome for this type of analysis.
Yeah, and I was just thinking as you were talking about all these projects. How do you take on so many at once? I guess you personally. Are you hopping around between these projects, or do you have a team then that you run that kind of does their own thing and they're probably on different timelines? Just curious to know how you, I guess, work with regards to so many different, interesting, cool things going on.
I have a very good team and fantastic collaborators. So, it's not a one-man show, as you have alluded to. In particular, the DOE labs, it's a highly interdisciplinary work, and we work with the domain scientists, we work with other stakeholders, we work with the university. So it's a collaboration between wide range of people, and that makes these projects very, very interesting. And one day you work on the fusion reactor project, another day you will be working on a natural language processing pipeline, another day for compiler optimization using artificial intelligence for supercomputers. and another day reinforcement learning for nuclear reactor control. And that makes this job very, very interesting. The full credit goes to my collaborators and my team.
Yeah.
It's definitely not a one-man show.
Sure. But you do get a chance to sort of touch all those things when you're working at the Argonne National Laboratory. It's not like stay in your lane and you just sort of focus on one thing for 5 years.
Correct. That's the beauty of National Lab. There is a huge interest and push towards adapting and using AI to accelerate scientific discovery. And in that context, the automated machine learning is something that is relevant for a wide range of applications. So everyone needs to develop models. And that's where we come in, like, okay, so how we can sort of formalize this whole process. And once we formulate this, then we can think of solutions to address this problem. And that's where our supercomputers are coming in. And because this problem requires scale, this is not about, okay, training a billion parameter model on large amount of data. Even if you have a small data, the automated machine learning methodologies that we are developing, we explore thousands and thousands of models in just 2 hours, right? So in 2 to 3 hours, we can explore thousands of models for a particular data set and come up with not one best model, but hundreds of really good models for that particular data set. I mean, of course, we do have large data for which we have to scale up this, but even a small data set requires a scale because the number of possible models that you could explore in this space is really huge, right? And another thing to note here, the reason why we are interested in developing a lot of models in a very short period of time is that unlike other settings in the industry, most of our problems are inverse problems in the sense that we have the output and we have to go and see what is the input. This is what we call sort of inverse problem, where you say the diffraction pattern from X-ray. So you take a material, you send the X-ray towards it, and you will have a diffraction pattern. And what you observe is a diffraction pattern, not the material. So from the diffraction pattern, you need to go back and reconstruct what is inside the material, right? So that's the inverse problem. And the inverse problems are notoriously hard, which also means that you have not one solution, you have multiple solutions. And that means developing one single model for this data set doesn't make a lot of sense. You need to have hundreds of models. From those hundreds of models, you can do inference for those inverse problems and then combine all those results to make sense out of it. And more importantly, uncertainty quantification is a must-have property for many of the problems that we are dealing with. And developing these type of models are quite important. So it's not about just building one model that can do well. It's about building hundreds of models that can do well on the data set and then use those models and combine them to generate results.
Yeah, for sure. I mean, you guys do stuff with, well, I guess a couple thoughts that I had right now. One was, are you doing a lot of essentially unsupervised learning where you're not tagging a bunch of stuff, you're just sort of running it through and trying to decipher what the right weights and measures would be for the neurons in a deep learning? Or are you guys dealing with tag data? What's most of the data that you're dealing with?
We have a wide range
Okay.
of applications and wide range of modality, as you pointed out. Like for some problems, we don't have labeled data, and we have to do a lot of unsupervised learning, in particular, trying to learn latent representations and make inference out of that latent representations, or use that and combine that with the physics knowledge. So one thing that I also want to point out is, like, again, the science setting is in that way it's good because in many applications we know a lot about the underlying domain, right? So you have physical models and you can use those physical models, or you have a simulator. That simulator can be run in different fidelities, like low. Even if you take the climate simulation, it's to run it at a very high resolution, it's very, very expensive. So they cannot afford more than, let's say, 10 simulations. On the other hand, if you want to run it at really low fidelity or lower resolutions, then you can run many more. And that presents interesting challenges as well. So how can you use a lot of low resolution simulations, learn from it, or learn the representations and dynamics and physics from it, and physics knowledge into those type of models using loss functions or in the architecture, then take that to the high resolution where you just calibrate your low resolution model to the high resolution model, right? So those are the things. So yeah, labeling is a big problem in many settings, in many science settings. Labels are expensive, hard to come by, or you have to do physical experiments. That's not only time consuming, but it's also, it costs. There are other domains where you have a lot of labels, and there the data could be, the data volume could be could be an issue. And the point is, in some settings where the data collection happens at a speed that you cannot just afford to move that much data from one experimental facility to the computing facility, like in the cloud, and do that in the cloud and send the results back. You have to do that at the edge, trying to see, whether the results are good or bad, and how to do that. One way is to do just train the model offline and move it to the inference. That sort of modality works for certain settings, but in several other settings, we have to develop continual learning methods where the data comes in and you have to continually update your model on the fly to make it more efficient for the particular experiment, for the particular sort of modality and materials and so on and so forth. So I'm saying that there is a wide range of problems and wide range of challenges that we have to overcome.
Yeah, for sure. Now, you guys run your own data centers, I'm guessing. I mean, all your data is probably very sensitive information. So you kind of have to build this infrastructure completely in-house with your team. Is that correct?
No, we rely on a number of infrastructures, data movement infrastructures and compute infrastructures. There are research that deals with sensitive data like health and so on and so forth, that we have sort of, secured enclaves. But most of the research that we do here at Argonne are sort of open in nature. It doesn't mean that we can just move the data outside, but it's an open research. The research will be sort of, disseminated to the public once the data is verified and so on and so forth. But when it comes for learning, right? So when it comes for developing models and doing machine learning on this data, there are different types of constraints associated with the data. One is just the volume. You have to post the data, you have to move the data to the compute center. So some of the experimental facilities we have, some of the processing can be done there, but there's also infrastructure, data movement infrastructure called Globus, which is a flagship product of Argonne. It's used widely in the research community to move data from one place to another place, large amount of data without doing, let's say, SCP over your terminal and hoping that it doesn't end abruptly, right? So those type of research infrastructures exist. And also we have ESNet. It's a DOE infrastructure for data movement from one lab to another lab or from across universities. It's a very solid infrastructure. A lot of research went in before the AI boom. So now we are leveraging those type of infrastructures, both the compute and the data movement infrastructures for AI, which is sort of, helping us to do these kind of data movements across geographically distributed sites.
Yeah, sure. Yeah, I guess I was curious if you guys run your stuff on large public clouds like Amazon or Google or Microsoft Azure, or any of that type stuff.
So since we have our own computing infrastructure, majority of the research that we do sort of, targeted at these type of computing infrastructures. But there are some research groups that are also trying the public clouds and how to use public clouds for various types of purposes. And particularly, this is coming from the stakeholders. For example, the projects, some of the projects that we have, those are on traffic forecasting. And the traffic monitoring centers want to use the models. And for them, using the DOE supercomputing infrastructures will be too much. On the other hand, if you say, okay, we develop the model and we can host somewhere in the cloud, that will be easier for them to just write an API and pull the prediction. Or they can even host the model inside their TMC centers if they have an infrastructure or a smaller infrastructure, right? So there are multiple benefits for these things. When it comes for the supercomputers versus clouds, right? So those are designed for different purposes, although the gap is becoming smaller and smaller. The DOE machines are sort of custom designed for science applications. So in the sense that, we want to run simulations because simulations play a major role in various scientific domains. And those type of simulations need a really tighter or high-performing interconnect where you have data moving from one node to the other node in a much faster way, right? And that is critical for HPC or high performance computing simulations. Although machine learning requires those kind of things for certain applications, in particular, if you are trying to do distributed data parallel training or model parallel training. So large models or a large amount of data, we need that sort of, a good interconnect that connects these nodes and can move data in a much faster way. And the software stack and the hardware is sort of architected in such a way that, it's a long process where the vendors and the DOE community worked together for several years to design these software stack and the hardware. So the hardware are sort of customized for the DOE applications, whereas the cloud is primarily for the public consumption. Let's say, ML models, large language models or vision models. But let's say for us, it's, we look at graph neural networks, point clouds, manifolds. And if we need customization, how can we do that? And in some of our applications, we need the learning to happen very closely to the simulation and while the data is being generated from the simulation. So those kind of things we can do very well because we design that system taking into account all these applications within the DOE complex. So that's why doing certain things on these large DOE supercomputers is beneficial.
That's a great distinction with regards to where a supercomputer lives and what it's the best thing it does versus if somebody were to go out to a public cloud and start up a Linux virtual server, for example, and run some stuff there. That's a completely different apples to oranges. And it reminded me, actually, the University of Minnesota has a really, actually, it's one of the first places, I think, to actually have a supercomputer. And I took a tour of their lab. This is probably 3 or 4 years ago, but it was really cool to walk through there and realize that, there were all these simulations going on, but, and it looked like one computer, but really under the covers, it was a lot of different other, there was a number of nodes working in conjunction with each other to essentially crunch data, right? That's really what, at the end of the day, it's like a Ferrari, it's like a sports car just for crunching data. You wouldn't want to use it to serve up a website, right? So it's completely different application for it.
You're spot on. Again, it's primarily the applications that drive these designs, and the cloud is sort of designed for a larger user base, whereas the supercomputers are designed for a class of applications and taking those scientific application specific constraints into account.
Cool. What's changed in the past, I would say, 5 to 10 years or so with regards to making things move a lot faster, right? I'm sure we wanted to take a look at models regarding, nuclear reactors, right? And build those models 30, 40, 50 years ago, right? But what's changed in the technology to now allow us to be able to do what you're talking about today?
Our ability to collect data from, let's say, if you're talking about this energy reactors, we can collect a lot more data from the original reactors. At the same time, our ability to simulate larger and larger reactors is also increasing thanks to the computing power. So simulation, data collection capability, and basically the computing power that allows us to do both. All these factors allow us to now look at this type of advanced methods to do control, disruption prediction, and so on and so forth. And also, a lot of credit should be given to the AI ML community for pushing the boundaries and pushing the envelope. So we are just standing on the shoulders of the giants. We owe a lot to the applied math community, and Argonne has a fantastic applied mathematics community, which we benefit a lot from, and also within DOE complex and other applied math community, right? So it's advancement in mathematical optimization, advancement in computing, advancement in AI and machine learning. So all these giants helped us to push these fields forward, and we owe a lot to them.
Yeah, I'm wondering if it was if there was a switch that was flipped, that all of a sudden we have everything we need, but it feels like it was just more or less everyone sort of marching in line. Obviously GPUs, I think, probably changed the game a little bit. Like you said, maybe there's some new algorithms that were developed, I guess, with regards to deep learning. But yeah, I always sort of ask people that, like, kind of what are the advancements that sort of have led to where we got to today in our field? It sounds like a little bit of everything. Where do you see this thing going in the future, I guess? Where can we push the envelope further, you think, in the next 5 to 10 years?
The future looks very, very exciting. In particular, ability to accelerate scientific discovery using advanced AI ML methods. So that's a frontier. And it's sort of like technology similar to computers, like how computers sort of transformed our lives, right? That's the sort of potential that AI ML can have in scientific applications. So it's not like you can specify like, okay, this one application, but it's the entire spectrum of applications. And that's why the research community is quite excited about bringing these type of methodologies into their pipeline. And previously it was theory, experiments, and observations. Now theory, experiments, observations, and it could be the fourth pillar is this AI, ML, right? So that's the sort of importance that it is getting. But as we move forward, AI/ML, it's not a fancy thing to apply in your method. It's much more like it'll become more a foundational building block within science, and that can sort of accelerate the way that we do science, because scientific discovery is very time consuming, very expensive, and a lot of manual effort, trial and error efforts. So that's an area where AI/ML can really help scientists to advance the field in a way which is otherwise not possible.
Yeah, for sure. Well, it sounds like some really cool things are happening at the Argonne National Laboratory. Are you guys hiring? I always like to ask people if they're working, whatever organization they're working for. Are you looking for top talent? And if you are, where should people go?
Yes, we do. We are looking for people in the field of AI/ML in wide spectrum. So starting from postdocs all the way up to scientist level. So there are a wide range of open positions. We also engage with universities, try to bring undergrads, master level students, and we have a fantastic internship program for graduate level students. And particularly, we are looking for opportunities to engage with underrepresented communities and bring them into the lab and expose them to the scientific advancements, so that we have some sort of constant pipeline of talents coming in. Diversity is becoming very crucial for our advancements as well. So there are a lot of efforts on that front. So there's a wide range of opportunities, and there is a career page at Argonne. People can go and check that out. And there is also internship programs. They have specific web pages. Math and Computer Science Division has a separate page for those type of internship opportunities. And I highly recommend the listeners, if you are interested in, please check out those web pages or reach out to me. I'm happy to make connections.
Awesome. That's great. And yeah, we'll definitely put links to your careers page here in the liner notes for the podcast when we publish it. I also did want to make a quick plug here too, because you will be speaking at our Applied AI meetup on June 2nd on democratizing deep learning with DeepHyper. So we'll get a chance to dig more into the DeepHyper project. You guys are publicly funded, or I guess funded through the government. Is that correct?
Correct. We are mostly funded by Department of Energy, but there are also projects that are funded by Department of Homeland Security, NASA, and other agencies, including NSF, NIH, and so on and so forth. I'm
just curious, are there requirements for you to make your source code open because of the way that you're funded at all? Or I love it that DeepHyper is actually open source, right? You've got a great page there with everything. People can download, inspect everything, run a Google Colab, do whatever else they want with it. But are most of your projects open source or not? I guess I just don't know the regulations behind that. I'm just kind of curious. Often
it depends on the type of funding, but Argonne is primarily an open research lab. And most of the research that we do are open in the sense that we disseminate through publications and the softwares, technical reports, and so on and so forth after approval from Argonne. So the source code and open source culture is something very, very strong within Argonne, in particular the computing divisions. And, whether we do something, we put it in a notebook associated with the paper, because reproducibility is very, very crucial, especially in the area of AI/ML. And so that helps other researchers to take the code, reproduce the results, and use it in their own setting. So, and also the computing divisions, they have several flagship open source projects, and that sort of inspire us to develop such a kind of software. For example, PETC is a linear algebra, a library coming from our division, and the NEC 5K, it's another type of software. So these are all softwares that existed before, and there are new softwares that are coming up. So, this chain effect, right? So people inspire us to do more open source softwares, and we think that open source softwares are great, not only just for the visibility, but also for the scientific progress. And that's how, we benefit a lot from industry like Google and Facebook, PyTorch and TensorFlow. Without those software stack, we wouldn't be here, right? Everyone will be writing their own C++ code to do backprop, and that's not scalable. So, we again owe a lot of things to the industry, and we learn the best practices from them and the software stack. We benefit from the software stack, and we also do this for the others so that they can benefit in a similar way.
That's cool. I wasn't sure if you guys commercialize any of the stuff that you do, or are you more straight just research and publishing your findings?
It depends on the type of research and the type of project and funding. And there are separate channels to take open source projects or take the projects that are done at Argonne and take a commercialization road after that. So it depends on people. And there is also licensing opportunities for companies to get the IP from Argonne and use that in their product and things like that. So there are a wide range of commercialization aspects. And in particular, DOE is interested in helping small and medium scale businesses to benefit from the research that we do. And there are separate channels within Argonne and within DOE to help those kind of things. But right now, we are primarily the computing applied math divisions. We primarily focused on open source research so that the community will benefit. And particularly, we are interested in sort of pushing the boundaries of scientific discovery using AI/ML. That's where we are.
That's awesome. No, that's so cool. And I mean, I will say just to the people, the listeners, I love that I sent a message into the Argonne National Laboratory and actually got a response pretty quickly from you guys with regards to wanting to share what you're doing. And, I don't have a lot of experience, I guess, talking with anybody in national research organizations or whatever, but I really appreciate your time being on the program here, Prasanna, and sharing everything that you do. My undergrad is in applied math. And so I really love to see the applications, and kind of that's why I got the idea of applied AI as well, is just the applications of all this technology. And I know you guys spend a lot of time not only thinking, but also computing, right? You guys have an entire laboratory and spending a lot of energy, I think, trying to make the best solutions that you can that then will, of course, benefit, like you said, the scientific community, abroad. So I love your mission. I think it's really, really cool. And thank you so much for being on the program today. Is there any other thing that you wanted to maybe share at all that I might have missed, or did we cover most everything you wanted to talk about?
I think we covered, most of the things. And again, there are a couple of things, things on energy efficient computing, like alternate forms of AI, neuromorphic computing. We are looking into ways to sort of how to develop energy efficient AI/ML methods that can work at the edge, which is a lot more bio-inspired as opposed to backpropagation based or gradient based methods and related things. But probably, we can save it for another time. I think we covered a lot.
Have you heard the term TinyML? I guess I'm not sure if we had talked about that.
Yeah.
That's a huge interest of mine, and I'm actually going to be teaching a class here at the University of St. Thomas that's really around that. I've taught an IoT class for many years, but I want to bring in the machine learning. And when you start talking about running at the edge, my mind went sort of right to TinyML, running these, very low power.
Yeah, exactly. Yeah, that's a very big piece of the whole puzzle that we are looking at. So it's great that you are teaching course on that. So, I think that's the sort of a very promising next frontier in AI/ML, not just for the inference, but how can we do tiny ML at the edge with learning and do that more personalized things, right? So a particular instrument, ML for a particular person, right? It just opens up so many new possibilities and things that we can do.
Yeah, for sure. Well, maybe I'll have you back on, I guess, here in a couple of months or so, and we can talk about TinyML, all day. But yeah, I that is a very cool part of where I think a lot of this technology is going, is to run it more and more personalized. So really, like, you have that digital assistant with you, and that can be very, very powerful for people. So, well, thanks, Prasanna. Again, I appreciate the time today. This has been great, and look forward to having you at our next meetup on June 2nd. We'll talk more about DeepHyper. But yeah, thanks again, and let's keep in touch for sure.
Thanks for having me, Justin. Thanks for the opportunity.
You've listened to another episode of the Conversations on Applied AI podcast. We hope you are eager to learn more about applying artificial intelligence and deep learning within your organization. You can visit us at appliedai.mn to keep up to date on our events and connect with our amazing community. Please don't hesitate to reach out to Justin at appliedai.mn if you are interested in participating in a future episode. Thank you for listening.